So the next paper is FlyMon, enabling on-the-fly task reconfiguration for network measurement. This work will be presented by Hao Zheng, who will be available for remote Q&A after the talk. Hao Zheng received his BS degree at the Department of Software Engineering, Southeast University, China in 2020, and he is a second-year PhD student in the Department of Computer Science and Technology at Nanjing University in China. His research interests include software-defined networks, data center networks, and network measurements, and the artifacts associated with this paper have been evaluated as reproducible, and the reference implementation of FlyMon has been released as open source on GitHub. Can we run the video?
Hello everyone, I'm Hao Zheng. Today I will talk about our recent work on network measurement. This is a research project of Nanjing University and Peking University, China. FlyMon is a measurement system that can make on-the-fly reconfigurations among a large set of sketch-based measurement tasks. Let's first read some background. We know that network measurement is important. In most network environments like DCN and WAN, operators need to perform many management tasks on network, such as traffic engineering and performance diagnosis. Most of these tasks rely on real-time measurements of underlying network traffic. For example, the heavy hitter detection is important for traffic engineering and anomaly detection. According to the monitored statistics or events, operators then make management decisions to address congestions or anomalies. What are the measurement tasks? We use a new abstraction in FlyMon. We define a flow-level measurement task is composed of a flow key and a flow attribute. For example, heavy hitter detection can be abstracted into taking 5 tuples as the key and frequency as the attribute. Another example is DDoS victim detection. It can be abstracted into taking test IP as the key and counting distinct number of source IP for each test IP. Here, the distinct is another flow attribute. So, there are many flow keys. They can be any combinations from different protocol fields, even bit-level prefixes of the fields. And there are several common flow attributes. Each of them can derive a variety of measurement tasks. Then, the set of measurement tasks is the Cartesian product of the key set and the attribute set. Currently, sketches are popular for measuring flow attributes due to their memory efficiency and accuracy. Different sketches focus on solving different flow attributes or measurement tasks. So, the measurement system must implement multiple sketches to meet the diverse measurement demands. However, the task capacity in hardware switches is limited. Conventional implementation of sketches occupies exclusive hardware resources on programmable switches. Take the RMT-based implementation of countermean sketch as an example. Packet fields are stored in the packet header vector. If we take the source test IP pair as the flow key, the two fields are input to the hash unit to get a memory index. To update the countermean sketch, the SLU increases the counter addressed by the hash index. This implementation cannot change the hash inputs, the SLU operation, and the memory configurations including size and bitwise. We evaluate the resource footprint of a countermean sketch with 5 rows and 80,000 counters for each row. We found that using the whole resources of an RMT switch cannot support more than 6 sketches in this common case. So, the task capacity in hardware is very limited. It is impossible to configure all needed tasks in a hardware switch. According to the above discussions, it's challenging to support all required measurement tasks in hardware switches. So, the task reconfiguration is necessary for a practical measurement system. The first case is when we try to meet the changing measurement demands of tenants or applications. As the time goes on, new tenants or new applications from existing tenants may need to deploy new measurement tasks in the network. Besides, existing measurement tasks may also be replaced or updated. So, measurement task reconfiguration can timely and accurately meet the changing measurement demands. The second case is when we need to fast locate the root cause of ongoing network anomalies. Suppose a user complains that the poor network performance affects their web services. The operator then uses the measurement system to diagnose all related devices to gradually locate the root cause of the problem. Measurement task reconfiguration brings more visibility of the network by giving more statistics. Existing works make great contributions to support more tasks in switches. The first kind of solution is to design general or versatile sketching algorithms. They can be divided into multi-attribute algorithms and multi-key algorithms. However, it's hard to design a full key and full attribute sketch. The second kind of solution is to use the compile-fit programmability of RMT switches to change the hardware functions. However, it will interrupt running network traffic to reload the data plan code, so it is unacceptable for online monitoring. Below are our designs. The target of FlyMon is to enable on-the-fly reconfiguration of sketch-based measurement tasks. We divide the target into dynamic key, dynamic attribute or sketch, and dynamic memory. Our designs are based on RMT-based hardware switch. The basic idea is to compose the task implementation with mesh action tables. In particular, we propose three basic parts in the data plane: a case action phase, an attribute operation phase, and address translation mechanism. The control plane can configure the three parts as various measurement tasks by adding or deleting the table rules of the three parts. We define the three basic parts as a composable measurement units, abbreviated to CMU or CM unit. Below are our design details of the CM unit. The first part of a CM unit is the case action phase. The basic implementation is to allocate some bits called dynamic key in the PHV, which is used as the fixed input of the hash unit. We can dynamically select an input key from the candidate case through a match action table. However, there is a critical overhead on PHV occupancy. We name the overhead as PHV copy. If we want to spot 5 tuples as a key, we must statically allocate additional 104 bits in PHV for each CM unit. However, PHV is precious resource in RMT hardware. To optimize it, we introduce a list copy strategy. Firstly, we generate several compressed keys with hash units. We can decide which keys to compress in the control plane with the dynamic hashing feature of the RMT hardware. Secondly, each CM unit only selects the compressed keys or the bitwise exclusive OR among the compressed keys. With the optimization, we can deploy about 5 times CM units when the candidate key size reaches 360 bits. The second part of a CM unit is the attribute operation phase. Since each SLU can accommodate multiple stateful operations, we also use a table to select different stateful operations for various measurement tasks. A challenge here is that there are limited preloaded stateful operations. The sketches that need to be spotted are more than the number of stateful operations. Firstly, we choose some sketches as FlyMon's built-in algorithms. These algorithms are simple but dedicated to common flow attributes. Our main optimization here is to use the reduced operation set to implement the built-in algorithms. The generation process of the reduced operation set includes 2 steps. Firstly, we decompose the algorithms into data plane operations and control plane analysis. We find multiple algorithms can share some joint operations. Secondly, we aggregate some simple operations into one stateful action. Finally, FlyMon used 3 stateful actions to implement at least 10 sketches. For the detailed implementations of the built-in algorithms, please read our paper. FlyMon provides 2 levels of dynamic memory. Firstly, each CM unit can switch to any supported measurement tasks with the case action phase and the attribute operation phase. Thus, we can achieve unit-level memory management by adjusting the number of CM units for the measurement tasks. However, since the number of CM units is limited, it cannot achieve fine-grained memory management and only supports a limited number of concurrent memory tasks. We implement sub-unit level dynamic memory inside the CM units through an address translation mechanism. The sub-unit level dynamic memory brings more flexible memory allocations and can accommodate more memory tasks with isolated memory. Please see implementation details in the paper. Based on the above discussions of CM units, here is a complete view of CM units in the RMT pipeline. Each CM unit has 4 stages. A compression stage performs one-way compressions on the candidate case. An initialization stage sets the flow case and other parameters for this CM unit. A preparation stage completes the address translation. It can also process the select parameters, which is essential for implementing some algorithms. Finally, the operation stage updates the memory according to the stacked and processed key and parameters. Note that the compression stage and the initialization stage belong to the case detection phase. The preparation stage and the operation stage belong to the attribute operation phase. Yet, the address translation mechanism is implied in the preparation stage. To place more CM units in the RMT pipeline, we arrange multiple CM units in a grouped fashion. A CMU group is a set of CM units. These CM units share a compression stage and are deployed in parallel. Further, we cross-stack multiple CMU groups in the RMT pipeline to increase the number of deployed CMU groups in given MAU stages. Please read our paper for details. Then we talk about our implementation and evaluation results. We implement FlyMon on a Twino-based hardware switch. In the data plan, we use around 5,700 lines of P416 codes to implement 9 CMU groups, including 27 CM units. In the control plan, we use around 3,000 Python codes to implement the on-the-fly reconfigurations of all built-in algorithms. Besides, we also implement other essential components such as the resource manager and the task manager. We also implement a simulation framework for accuracy testing. We evaluate FlyMon on functionality, resource usage, and accuracy. Due to the time limitation, we only show part of the evaluation results. Firstly, we found measurement tasks can be deployed at the millisecond level. FlyMon has good expressiveness. One CMU group is sufficient to support 4 common flow attributes. We also evaluate the impact of reconfiguration events on traffic forwarding. We use iPerf to generate TCP traffic and measure the throughput of the traffic. We found FlyMon has no side effect on traffic forwarding. In contrast, the compile phase reconfigurations will interrupt the traffic for several seconds. We evaluate the resource usage of FlyMon by integrating CMU groups into Twino's baseline switch project, switch.p4. We found more than 3 CMU groups can be integrated into switch.p4. We found the average resource overhead of one CMU group is less than 8.3%, and the hashing resources are the bottleneck. For the overhead of address translation mechanism, we found the TCAM cost of 32 memory divisions is less than 13% of one MAU stage. With the less copy strategy, we can deploy more CM units when supporting larger candidate case. To conclude, FlyMon achieves on-the-fly reconfiguration of sketch-based measurement tasks. It supports on-the-fly task deployment at the millisecond level. It supports at least 4 common flow attributes and 10 algorithms. It also supports dynamic memory management. Our reference implementation of FlyMon is available at GitHub. Thanks for your listening.
Thank you. Do we have questions in the room? I'm looking. If not, I have a question. First of all, thank you for your talk. If you have a network where you have multiple programmable switches configured, could you does your system also allow for orchestrating measurements for traffic that passes through several switches in the network? And if so, how does that work?
Okay, it's an interesting question. Our current design mainly focus on the single sketch design, but switch design, but it also works for network-wide measurement because existing works on software-defined measurement also propose some measurement system to solve the network-wide measurement problem. If we just use multiple programmable switches, we can change these switches because we can inject some metadata into the package, and the downstream switch can use this metadata to perform the measurement.
Okay, thank you. Looking in the room, are there more questions? Yeah, there's a question in the back. Go ahead. No sound? Can you try again? No. Yeah.
Oh, okay.
That's perfect.
So I have a question. So when you use your runtime APIs to switch the tasks in your switch, is there any overhead?
No. To reconfigure the measurement task, it's just like you adding a routine table. It just not affect the traffic forwarding because it is not on the forwarding path of the data plane.
Yeah, actually, just for example, just like you have 3 tasks in the switch. Now you would like to switch one of the tasks to another task. Actually, what I mean is that is there kind of overhead when you switch one task to another task? Because you cannot add another task because at the most 3 tasks in the switch.
Okay, the resource occupancy in the RMT switch is static after you running a switch. So if you want to reconfigure a new task, you must first delete existing task if all same units are allocated. But if there are unused same units, you can just configure it to the task you require, you want to deploy it.
Okay, is there kind of like latency?
I think I saw one other question.
I think the latency in our evaluation is less than 100 milliseconds. But once the task is deployed to the hardware switch, the terminal can pressure that the switch is running at a line rate. It's around Kbps level. Okay.
Okay, thank you.
Yeah. Time for one more quick question. I thought I saw one. Yes, there at the back.
Hi, Shir from the Open University in Israel. Great talk and a great work. I wanted to know if you guys have thought about the need to clean the structures between the reconfiguration, if that's something that is happening, or have you guys thought about that?
Sorry, could you repeat your question?
Sure. So if you're using the same memory for different tasks, you may need to clean the memory between the reconfiguration of the different tasks. Is that something that is currently done by the system, or have you guys thought about that at all?
Okay. First, the task could work in different memory range. We call isolated memory. But if the memory must use single memory because to replace the old task, we must clean the data in the new epoch, memory epoch.
And this is done by the control plane? Or?
Yes, it should done in the control plane quickly.
Thank you.
Okay, let's thank the speaker.